Now, when using deductive reasoning with algebraic solutions, okay, and if we want to call this mathy types, okay, solutions, we can generalize numbers using variables that show that no matter what numbers are used, the conclusion always follows a pattern. So I just want to quickly slide back to what we did in a previous lesson here with the difference between perfect or consecutive perfect squares is always an odd number. Okay, what we did is we took some examples that we knew. So we found perfect squares, we took ones that were side by side, subtracted them, and we came up with a conjecture based on what we saw, based on those facts. Now, we can also do that using deductive reasoning, but deductive reasoning means that it must always be true. Okay, so we can't just see that it looks like a pattern is forming. We actually have to figure out that it is always true and that it's always there. So example number 8 here, what we're going to do is we want to again prove that the difference between consecutive perfect squares is always an odd number. Okay, and we're going to do this algebraically, and this is where it can become a bit confusing, and this is where we actually, some people might say, where's the math in all of this logic? But this is where we're going to come in with what we would normally consider to be math. We're going to bring algebra into this case. Now, any number can be considered a variable, okay? So we're going to call any number to be x, okay? We're going to use x in a lot of these situations, and any number is going to be x, okay? So this is going to be our starting point in many of these situations. What we want to do is prove the difference between any consecutive perfect squares is an odd number. So we want to take so consecutive squares, and I'm just reminded that what we had here, it's 1 squared, 2 squared, 3 squared, 4 squared, and so on and so forth. To get, and then the answers are 1, 4, 9, and 16. Okay, so remember, that's what we did with consecutive perfect squares. Now, to get this in an algebraic sense, what we can do is we can take a number and square it. So that's what we're going to do here. We're going to take the number, any number, just could be 1, 2, 3, 4, and we're going to square it. So this is our first value, or perfect square. Okay, x squared is a perfect square. The next consecutive one, so if we started with 1, the next one is 2. Okay, the difference between x and the next one is going to be x plus 1. That is our next number. If x is 1, x plus 1 is 2. If x is 3, x plus 1 is 4. They're consecutive numbers. They're one after another. So this is a way of algebraically saying that we have two numbers side by side, x and x plus 1. And if we want to find the next perfect square, we square that. So this is our second perfect square. Okay? And we want to find, is the difference between these two an odd number? Well, it's going to be important to understand algebraically what an odd number represents. And so what we'll do here is we're going to solve this, and we're going to do a subtraction statement. So we're going to subtract x plus 1 squared minus x squared is going to equal something. And we're hoping that it is an odd number. Okay, and we're going to do this algebraically, as you noticed. Now the x is just what we use. Some people will use n for any number. You can use any letter you want. I use x. To do this now, we're going to, again, use the algebra that we took a look at last year back in grade 10. Okay, hopefully we remember that. When we see x plus 1 squared, okay, we can use the distributive property to know that this is x squared plus x plus x plus 1. Okay, so that's x times 1 plus x times 1 plus x squared plus 1 squared. Okay, so that's how we come up with that. And this is minusing x squared. And still we're not sure what it's going to equal. If we combine all of our like terms, we have x squared plus 2x plus 1 minus x squared is still equal to our question mark. We don't know. So that's combining this here. Now we can subtract like terms, or I guess put together like terms. We have an x squared and negative x squared. This is going to become 2x plus 1 is equal to our answer. Now some of you are like, well, what does that have to do with our perfect squares? Well, what we're doing is we're trying to simplify down as far as possible. This polynomial can't be simplified any farther. This expression, okay, 2x plus 1, represents, if we take a number, 1, okay, and plug it into here, what is our answer going to be? And I'm putting question mark as the answer right now, and we're hoping that that's an odd number. Now, so let's go back to what we did prior when we did inductive reasoning. If we did 2 and 1, so I'm just going to flip this back over. 2 squared is 4, 1 squared is 1. So 4 minus 1 was 3. So if we do 1 and 2, we start with the low one. That was our first number. Second number is added. So if we put 1 into here, 2 times 1 is 2, plus 1 is 3. Gives us the same answer. Okay, if we did that with 2 and 3, 2 times 2 is 4, plus 1 is 5. Well, the difference between 9 and 4 is 5. Okay, so it ends up working. Now, to know that this is an odd number, okay, is a little bit more of a second step here. 2x is always even. If we multiply a number by 2, it's always even. When we add 1, get rid of that. That was going to be positive 1, but we'll do add 1. When we add 1 to an even number, it becomes odd. Sorry about the announcement there. That is part of the school day that we're going through today. So 2x is always even, so that's 2x. If we add 1 to any even number, it becomes odd. Okay, so this is always an odd number. It doesn't matter what number we start with our perfect squares. When we solve it algebraically, we're always going to get an odd number, meaning that this conjecture works out. Okay, we can prove that deductively. This is proving deductively.